So let's look at these two Lewis structures that for sulfuric acid. One on the left here, and I put in all the lone pairs around in this structure. We'll call this structure A. And this other structure that you may not have guessed from following the normal Lewis structure steps, and we'll call this B. So why does this structure seem to follow all the experimental data? The experimental data said that we had smaller sulfur-oxygen bonds in this position, but regular sulfur-oxygen bonds in this position where the O is attached to the H. And this structure may agree with that. This one does not agree with that because these are all single bonds here, and so this structure would predict that you would have all the same sulfur-oxygen bond lengths, which it doesn't. It does have smaller bond lengths in these positions without the hydrogens attached to the O. So there's something called formal charge, and basically it's acting as if all the elements have their own Lewis own electrons, own valence electrons. How many extra or less it has is the formal charge. So to calculate the formal charge for each element, we take the number of valence electrons, subtract the number of bonds, and then subtract the number of unshared electrons. So basically this is how many valence electrons it starts off with and how much it shares with other elements or not. And so if we look at the hydrogens in both structures, they're both the same. They have both the same number of bonds to it. So we're going to calculate it just for both those sets of hydrogens. So if I do that, I take hydrogen and it has one valence electron. It's both attached to one bond, and there are no unshared electrons around the hydrogen, so I get 0 for the formal charge for hydrogen. And then the next element we'll do is this oxygen that has two lone pairs, and it has two bonds to each in both structures, the one that is attached to the hydrogen. So if I look at this oxygen with the two lone pairs, it has 6 valence electrons and it's attached to 2 bonds here, and then it has 4 unshared electrons. So 1, 2, 3, 4, not 2 pairs but 4 unshared electrons. So 6 minus 2 minus 4 is 0. So the hydrogen and the oxygen that's common to both structures all have 0 as their formal charge. Let's take structure A and look at the oxygen here, which is different from the other oxygen, which is the single oxygen connected to the sulfur, and they're both the same. So let's look at oxygen A. And if we look at that, we have 6 valence electrons for oxygen, and it only has one bond, but it has 6 unshared electrons, so we count those pairs as 1 each. So that's 6. So 6 minus 1 minus 6 is minus 1. So it doesn't have a formal charge of 0, it has a formal charge as minus 1. Let's finish structure A and look at the sulfur for A. And if we look at that, sulfur is in group 6. It has 6 valence electrons. It has 4 bonds to each of those 4 oxygens, but no unshared electrons. So look at the calculation. 6 minus 4 minus 0 is plus 2, which is good because, well, in a way that I have a minus 1 for each of the oxygens and a plus 2. So this we know is a neutral compound, so it does balance out to be neutral. However, let's go over here and look at structure B and the oxygens attached to the sulfur in structure B. It has a double bond and two lone pairs. If we look at the formal charge there, 6 valence electrons minus 2 bonds, and the 2 pairs we're going to count as individual, so 4 unshared electrons. So 6 minus 2 minus 4 is 0, so these oxygens have a formal charge of 0. Now let's look finally at the sulfur in this compound in the structure. It has formal charge of 6 minus 6 bonds, as you see those 6 lines, minus no unshared electrons, so this has a formal charge of 0. So it seems to indicate that the structure that has the lowest number of formal charges or closest to 0, like this one, would be the one that agrees with the experimental data. So perhaps there's a pattern there, and actually we see this repeated in other structures. The structure with the lowest formal charge will give the preferred structure.